welcome to everyone who's joined. It's my great pleasure to be the moderator for this evening's activity, which is the third iteration of Unboxing Quantum, our series on demystifying the research that's done at the Quantum Matter Institute and the physics of quantum more generally. My name is Alana Hallis, and I'm an assistant professor here at the Quantum Matter Institute, which is located at the University of British Columbia. And our topic for today, which was selected for its kind of spooky connection to the season being Halloween, has happened to be extremely fortuitous because if, like me, you enjoy following Nobel Prize announcements, then you'll have seen that this year's Nobel Prize in Physics, the 2022 Nobel Prize in Physics, was awarded to Elaine Aspect, John Closer, and Anton Zeilinger for the demonstration, the experimental demonstration of entanglement of photons, which demonstrates the violation of Bell inequalities, which has been very important for fields of quantum information science. And so if you, like me, are trying to understand what this Nobel Prize winning discovery means, and you've read some articles about it, you'll definitely have come across this phrase, spooky action at a distance, which was a phrase first used by Einstein to describe this entanglement phenomena. And that's exactly what we're going to be hearing about from our speaker, Ella Meyer, today. So Ella is the Quantum Computing Outreach Coordinator for Gearing Up, UBC's engineering outreach group. And she completed her bachelor's in astronomy here at the University of British Columbia. And Ella is focused on, in her work with Gearing Up, in lowering the barrier for young people to engage with STEM. So welcome to Ella, and please take it away.
Thank you so much for that incredible intro, Alana. I really appreciate it. I'm going to go ahead and I'm going to share my screen so you can all see the slides I have worked so hard on throughout this time. Here we go. Yes, as mentioned, my name's Ella Meyer. I'm the Quantum Computing Outreach Coordinator for UBC Gearing Up around the Quantum Matter Institute. I am the project manager for the Diversifying Talent in Quantum Computing Project, or DTQC. As Alana mentioned, the goal of the project is to do exactly what it says on the tin, diversify the talent pool entering the field of quantum computing. So with that, we try to engage a lot of students at kind of the K-12 level to first know that quantum computing, or quantum as a whole, is a field that exists. Secondly, it is not something restricted simply to Marvel movies for buzzword power. And third, it is something they themselves can do regardless of background, and that is a space that they belong in. And so, yes, as Alana mentioned, this is me. My headshot from the summer when I wore more color and it was bright out before, 7 p.m. Yeah, and I did my BSc here in astronomy. I did research at one point on radio astronomy and the cosmic microwave background. So if you ever want to talk about the beginning of the universe, send me an email. I could talk your ear off about it all day. However, the thing I'm here to talk your ear off about today is spooky action at distance. But before I get onto it, I would like to acknowledge that I am currently joining this call from the traditional, ancestral, and unceded territory of the Musqueam people. That is where UBC is situated. As you are all joining virtually, wherever you are joining from, I actively encourage you to learn about the land you are on. Look into territories, treaties. There are excellent resources online to give you more scope on that and to bring that forward as part of your learning. So as my overview, just so we all are on the same page of how this is going to go, we're going to start with an intro to what the heck is quantum mechanics to start with. From there, we're going to move on to talking about entanglement. That's where we're going to get into Einstein's bones to pick with all of the theory surrounding it, i.e. the EPR paradox. From there, we're going to move on into Bell inequalities, which were a big hot topic this year for the Nobel Prize. I like to think I manifested that topic into existence, or that them being the winners this year, because they knew I was doing this talk and wanted to give me something to go on. We're going to break down each section of the Nobel Prize, the three winners, how their work contributed to our understanding of quantum entanglement. And then we're going to talk a little bit about my favorite part of the field, which is implications going forward for things like quantum information and specifically quantum computing, which is what I am most interested in all of quantum. I will continue to flag this down as we go. So if you get lost, don't worry, just hang on. You're in for a good time. And so with that, this was the Nobel Prize this year. These three researchers got into experiments with entanglement, violation of Bell inequalities, and quantum information science. So 3 big topics we're going to think about today. And so how I like to think about physics, how I like to break down physics, is if we think about mechanics, i.e. things that can interact with each other, there are essentially 2 kinds of mechanics. There are the classical mechanics that you and I experience every single day, and there are quantum mechanics. Classical mechanics I think of as big physics. So the infamous, but probably actually not real, apple that whacked, Isaac Newton in the forehead, and then he was like, things fall, wacky bananas. That is classical mechanics, things that you and I tangibly interact with, the fact that I'm not floating away into the ether while giving this talk. And then there is quantum mechanics, i.e. small physics. And so when I say small, I don't mean small on the scale of like ant, I mean small on the scale of like 10 to the negative 10 meters. Inconceivably small to try to visualize, but something that actually has a lot of physics going on with it. So the behavior of particles, all particles, is determined by quantum mechanics. This includes interactions with other particles, measurability, their energy, spin, i.e. their, which you can think of kind of like intrinsic angular momentum, and so many more aspects of particles are best described by quantum mechanics. There are a few key ideas in quantum mechanics that make it very different from classical mechanics. And today we're going to look at my favorite one. As Elena mentioned, it's a little spooky term coined by Einstein, which is spooky action at a distance, i.e. how the heck are those 2 things connected? They're not talking to each other. Also, if you've seen any of the articles related to the Nobel Prize, this is the stock photo for quantum entanglement that comes up first on Google. The BBC beat me to it, but I chose it first. So I am going to do an example. This is about to get interactive. You can use the chat. So I need 2 people, or alternatively, I can play against myself because I can't actually see any of you, to do an example with rock, paper, scissors, which is hopefully everyone has done once in their life. So if 2 people could go ahead and tell me, I need you to play 1 game of rock, paper, scissors. And then I need you to tell me who won and with what. So I don't know, communicate, someone, you can count yourself down in the chat if you want to. 2 people can throw at the same time. And we can pick a pair of people who can do that. Alternatively, I'll do this against myself because I can't actually see anyone that is not me. So please feel free, or just 2 people can go in the chat immediately and just like type rock, paper, or scissors. Okay, so I've got 1 scissors and 1 rock from Sarah and Hannah respectively. So in this situation, we all know rock beats scissors. And so if I were to only have the pieces of information, hey, I just won this game of rock, paper, scissors, and I played rock, I know without having to ever have looked at the other person played scissors. And you're like, yes, that is how the game works. That is how the rules are established. And that is also how quantum mechanics works. And if this seems a little odd to you, I just need you to like hang on. We're going to get there. So once I have those 2 pieces of information, some kind of measurement, i.e. who won, and I know with what, I know what that thing was, I had instantaneous knowledge about the other piece of information, that 3rd piece, even if I personally didn't see it. This is actually super similar to entangled particles, where we can know things about this other part of the system without at any point having to wait. So for instance, if I was playing rock, paper, scissors against someone in the chat who lives in Calgary, none of you had to go there to actually know what happened, even if they didn't communicate it to you. And so that looks a little bit like this GIF, where we made a measurement. At one point, we were sort of like, we don't know who's going to win. We don't know what happened. 1 ball on the side of the screen turned blue. Instantaneously, the other one turned red because we knew how those 2 things were connected, and we can make that, we can like conclude that piece of information. So one of the things, one of the most common ways to explain this is if we had something along the lines of a cannon that has two dodgeballs in it. We know one is blue and one is yellow. We shoot that cannon off simultaneously. I catch a blue ball. I know you've caught a yellow ball. Exactly the same as rock, paper, scissors. And so particles work exactly the same way as our imaginary dodgeball cannon, or as this game of rock, paper, scissors I made you all play through the chat. Particles that are entangled, we have to describe them as part of a system, and they are so intrinsically linked we cannot describe one fully without describing the other. If we try to describe one particle by itself, we can only get into probabilities, but if we want to describe a full complete picture, we need both of these particles together. In the same way that you can't play rock, paper, scissors with just one thing, you need both. If we measure one of these particles, we can instantaneously learn information about this other particle, even if it is on the far opposite side of the observable universe. And if that sort of just made you go like, that doesn't make any sense, well, Einstein didn't think it made sense either. There is a really famous article that ran in the New York Times, here screenshotted, that's titled "Einstein Attacks Quantum Theory." He thought it was complete incorrect. There is a better reality out there possible. This can't be how things go. Later, he was a little about this headline, but like press is press. And so the way that he argued this couldn't be complete, this couldn't be correct, hinged on one very important equation that had come out in the 1920s, which is the Heisenberg uncertainty principle. And if you just saw this inequality and got kind of stressed, I'm not about to make you do any math. I just want you to think about two numbers potentially relevant to each other. And so what this looks like is in 1927, this was 8 years previously, Heisenberg, not the Breaking Bad Heisenberg, original Heisenberg, established a key quantum mechanics principle, which is this equation right here. And this tells you, deltas here just mean uncertainty and or sort of ness about one or the other. And what this tells us, this relationship right here, h and 4 pi are both constants, is basically we can either know the position with good accuracy or the momentum with good accuracy, i.e. if delta x is big, then delta p is small, or if delta p is small, then is big, then delta x can be small. They cannot both be small because they have to always be bigger than this other number. And so basically you can know how fast a thing is or where it is, but you can't know both of those things at the same time. And this was a founding principle for what became known as the EPR paradox. And so this was Einstein's rebuttal to quantum theory as it was first presented. And this is where I just need you to like, hang on, we're gonna get through it, and I think you're all gonna be able to get it. So these three scientists, Albert Einstein, Boris Podolsky, and Nathan Rosen, i.e. EPR, established a thought experiment that, proved or suggested quantum mechanics was incomplete. So in this case, we have two entangled particles. This group argued that if we could measure the position or momentum of one of them, then we could know that as well about the other one because of their entangled state. So we've made a measurement on one. We've said, hey, if we learn a piece of information about this one particle, we should know something about the other. And they go, oh, but if you know position or momentum, then we must know position or momentum about the other. So they had this thing called a criterion of reality, i.e. a hidden variable. Hang on to the phrase hidden variable. You're going to come back to it. So their criterion for this being real is if without disturbing the system, we can predict the value of a physical quality, then there must be some hidden variable in the system that corresponds to that quality. In the same way, if the imaginary ball I have caught, I can look at it and say blue, it had the trait somewhere in it that it was blue. So with this, if we're making this measurement instantaneously between the two and we learn a physical quality about one of the particles, information can't travel faster than light. We know that's true. Then the second particle must have definitive values for both of those things. Because if we could have made that measurement on either position or momentum and gotten either piece of information about the other end, those must have both been established in this other particle. But we can't have that. And Heisenberg told us so. And that equation is fundamental to most physics going forward. So how does that work? We've said that we could measure this and we would know that about the other particle, but then by its own rules, the second particle will have to have intrinsic values that it can't possibly have. So we resolved that through a series of steps, and that was actually the components of this year's Nobel Prize. So this goes into 3 key parts that we're going to look at through Elaine Aspect, John F. Closer, and Anton Zeiliger. So 3 components here. We're going to start with John F. Closer. However, so keep him in mind, he's gonna be the first person we go to. We're going to start with an idea called a Bell inequality. This is named after John Stuart Bell, who came up with the idea. And so, as I mentioned, we've got this intrinsic quality about the thing that we just might not be able to measure. That's giving it that information. This was called those hidden variables or criterion for reality. And so one of the things that, this is how one of the ways people try to explain the like sort of hidden variable situation was that it's not that we don't know that about it, it's just we can't measure it. It's containing secret information about the entangled particles that we as the observer just can't get to. But it is there, is the idea. And so the way Bell inequalities progressed from there is we said, okay, if we have outcomes that are dependent on these hidden variables, these hidden attributes about the particle itself, then there must be some sort of mathematical constraint on how the outcomes of 2 measurements are correlated. So if these 2 things are connected, there must be some way to mathematically represent that. And so this constraint became known as the Bell inequality, after aforementioned John Stuart Bell. And so this is the second and the last equation I will make you look at, I promise. So this is one of the standard forms of a Bell inequality. This one in particular is a CH-SH inequality. It's the one that matters, as far as I'm concerned right now, the most. And so the only part you actually have to understand for this is this number here, the absolute value of S is less than or equal to 2. I need to remember how to read inequalities. So this one value, S less than or equal to 2. And so so this is less than or equal to 2. Then we look at E, like these E, AB, E, AB prime, E, A prime B, E, A prime B prime. All those E's are just ways to look at sort of like expected values for different measurable experimental qualities. So if we measure experiment one way, we get AB. If we change one of the ways we measure it, we get AB prime. If you change the other one, A prime B, et cetera, et cetera. These are 4 receptors we could possibly have that would detect our information. And so we have the 4 possible combinations of those things. And so when we look at this equation and we think about all the different ways these values can come together and all the different ways we can detect things in the system, it predicts it to be greater than 2. If you look at it with hidden variables, it is less than 2. That is the whole criterion behind the Bell inequality. The whole idea is it has to be less than 2. And then quantum mechanics shows up and says, actually, I'm like 3 and a bit, which is obviously a problem. And so we had these 2 sort of ways we could look at it. And we're like, well, hidden variables says less than 2, quantum mechanics says greater than 2. And so we go to the lab and we experimentally test this. When we run these significant numbers of experiments, we take averages over time, we find that S is in fact greater than 2. Therefore, quantum mechanics is currently the best theory we have to explain what's going on. And all of the Nobel Prize basically just boiled down to a number is bigger than 2. And so, as I mentioned, we're going to start with John Closer and go through how we proved this, absolute value of S was greater than 2. So the first of the 3 researchers here, he developed experiments to test Bell inequalities, which one can imagine is quite difficult when you're working with fragile little entangled particles and multiple detectors. But when he did his experiments, we found consistently that we had this S value greater than 2. And as a result, these experiments supported quantum mechanics because it violated Bell's inequality. So he was like, hey, this value over time is consistently larger than this criterion that we set. So I don't think we can explain away quantum mechanics with just like, oh, there's hidden variables we just don't know about. However, there was a very key loophole in this experiment. He was sort of the first person to put it into experimental practice, but there was a hole in it that people could argue with. You know, got him a little bit of, I don't know if I should say flack about a Nobel laureate, but you know, people could ask questions about it. And sort of the question was, okay, you've put some sort of emitter in there that's going to let out these entangled particles. You've got a whole bunch of receptors, but the measurements and the receptors were all preset in this experiment. So someone could make the argument that the experimental setup in some way could have selected for some particles, but not all particles. Or there could be particles with hidden variables, and we're simply not detecting them. So they're saying, if you have this setup that's preset in this particular way, maybe your experiment has biases that where we're losing key parts of this information. And so everyone was like, oh, dang, that is actually a really big problem. How do we work around this? And then no one wanted to touch it because it was scary and complicated and difficult until we came to our second Nobel laureate, Alain Aspect. So when he was a PhD candidate, he was like, I'm not afraid of this, I gotcha. And he decided to further test this theory. So that was looking at ways to improve the experimental setup that previously had been established. And so what he did was he had this emitter in the middle and 4 detectors. And what he could do was, as soon as the entangled particles were emitted, he found a way to switch their direction. So they weren't, necessarily going out, perfect 90-degree angle or something. They're going slightly differently the second they leave the detector. But before they reached any kind of filter or way to measure them. And so in this way, the experimental setup could detect more particles overall because we had more detectors and we had potential particles going in multiple different directions. And so the saying that, oh, well, you're just not catching the particles that have this information became less valid because we do have a greater capacity to detect more of these particles in our experiment. The other thing is skeptics of this couldn't say, oh, well, you had a preset way you emitted them and a preset way you detected them. Those two things must be related. But they couldn't be anymore because the way it had been set up when it was emitted and the way the experimental setup was when it was detected were now different. And it was by billionths of a second. It was by tiny margins, but there was differences, which meant that this closed this really key loophole that it was quantum mechanics and not hidden variables, because we could, definitively sort of say, we think we're getting all the particles there. We don't think that we're missing any that had this information. And not only that, but we're able to show that the way we're emitting them and the way we're detecting them aren't in some way presetting any information. They're no longer related in any capacity. Which takes us on to our third Nobel laureate. So Anton Zeiliger conducted more tests on Bell inequalities, and he is credited as being one of the first researchers in the field of quantum information, which we're going to get to in a minute. So he used a wide variety of signals to control the filters and which way which filters would receive the particles, which way the particles were emitted, all of those different things. It started with things like random number generators to determine which way things were emitted. So there was no possible predictability in it. And then at one point he figured out how to use signals from distant galaxies to set off parts of his detectors so that it was truly far beyond his control. And even with these really, really distant signals, we started to see that, yes, this constraint always comes back, over large experiments greater than 2. It's not going to be hidden variables. We're really looking at this freaky real world of quantum mechanics. And so another really important piece that Anton Zeiliger worked on was exploring entangled systems with 2 or more particles. So we've been talking this whole time, up until this point, we've been looking at two particles at any given time, the red ball and the blue ball, the rock and the scissors. Any analogy you want to make about potential pairings, up to you, whatever pair works best for you. We've been talking about two. Well, what if you have more? What if you have 3 particles that are entangled? What if you have 5? What if you have 500? How do you make a system like that? How do those systems all talk to each other? Well, you know, are things different when you have more particles entangled? And this became a really key piece of the field of quantum information, which we're going to get into a little bit now. So congratulations, you now understand the Nobel Prize in Physics, or at least enough buzzwords to tell your friends you understand it. And so with that, we've pioneered this whole field of quantum information science. And quantum information science is what it says on the tin. It is quantum specific information, and we use that to do science. So through all these experiments, we've basically learned that quantum mechanics is potentially something we can utilize, and in 2 capacities. One is to better understand quantum phenomena itself, and the other is to develop tools utilizing these traits. And so, for example, if you're looking to study how particles behave at a very small level or how particles interact, you want to model that on a system that is as close to those actual things as possible, or with the actual things as possible. And so this is something that quantum information allows us to do. We can look at how actual particles behave very closely, and we can better describe those systems. The other thing we can do is develop these tools that I mentioned. So this includes my favorite part of the field, which is quantum computers. We also look at quantum algorithms, ways to do quantum encryption, and so much more. All hinges on this tiny little connection between particles. And so it's easy to ask the question, where does this take us? And so I want to talk a little bit to you about quantum computing. So we've talked about the fact that particles can be entangled. They are able to share this intrinsic information with each other instantaneously across large distances. So we could put a particle here and a particle on Mars, and as long as they're entangled, we can still understand things about that particle on Mars. And so one of the things we've done is we've taken quantum computers and harnessed them, and harness these abilities of entanglement and things like quantum teleportation and superposition, which I didn't talk about but are interesting, to be able to solve really complex problems that potentially otherwise were not solvable, or were solvable but like extremely slowly and not functionally solvable. And so this right here is a quantum computer. It looks like the most magnificent chandelier you've ever seen in like a rich person's house. I also got told yesterday by one of the Ars Ciencia artists that it looked like an upside down Tower of Babylon, which is a whole new comparison I've never heard before, but it does actually ring quite true after I Googled the Tower of Babylon. And so this whole machine right here, this multi-billion-dollar industry that we've started to look at, and huge amounts of research, has all started fundamentally because of things like entanglement and our ability to entangle particles in a machine like this. And using machines like this, using quantum computers, we're able to do these really interesting calculations and solve difficult problems. This specific computer is from IBM, but many of them have similar guts. So a few of these types of problems we are now able to solve utilizing something like quantum entanglement and quantum mechanics as a whole, is things like search problems. You know, searching for things like optimization paths. Those are the ones I usually like to explain the most. The most famous example that true quantum physicists sort of shake their heads at, what is the most accessible, is like the traveling salesperson problem. You have a given number of cities you want to go to, and you want to go between them efficiently, and you want to be able to visit each city once, and you want to close a loop. Just for an example, if you have 5 potential cities you want to do, there's actually 120 different routes to connect those potential locations. And so you imagine that scales pretty quickly. I think if you have like 13, it gets up into the thousands very rapidly. And so this is something that is not usually easily solvable, something a quantum computer has much better luck with. As I mentioned, one of the other things we can do is simulate quantum systems. So if we want to look at the behavior of particles or the way that different things are interacting, You want to do that on a system that most closely mirrors the actual situation as possible. And so if we're using quantum systems, we can better simulate quantum phenomena. Cryptography is a big part of this. Being able to encrypt and decrypt information is particularly important in this information age we are living in. Quantum computers give us new tools to approach this. There's also implications in things that are out of my wheelhouse, but absolutely fascinating, like computational biology, or looking at different ways we can simulate the foldings of complex proteins. It also helps us with drug development. It connects into machine learning and so much more. And this is all, again, fundamentally because we are able to entangle particles and they are able to share information with each other. And so if at any point I've lost you, I'm about to give you a rundown of everything I talked about so you can ask good questions. We started all of this with our intro to quantum mechanics, the fact that, you know, Einstein had a bit of a bone to pick with the idea of spooky action in a distance, and that classical mechanics deals with large things in our world. Quantum mechanics deals with the very small. These very small things, particles up into even actually now small diamonds, we are able to entangle. They're able to share intrinsic information with each other. They are part of a complex system that we always want to describe as a whole. And using that, they're able to do some really weird stuff we can't really explain away with things like hidden variables. From there, we talked about the EPR paradox, which is Einstein's rebuttal to quantum theory, saying that basically, if you could measure a physical quality about a particle and then know that about a particle that's entangled with, then that in some way must violate Heisenberg's uncertainty principle, but it doesn't. And so the way we proved that this, you know, was not an actual hole in it, there are no hidden variables, is we looked at Bell inequalities. Bell inequalities being, we just want that S to be greater than or less than or equal to 2, for it to hold greater than or equal to 2, for it to fail. And we established that by running multiple experiments over a long period of time, looking at the overall net result of all of our different receptors and all the different ways we can measure particles. Then we went through, we talked about the 3 different Nobel Prize winners this year who looked at quantum entanglement. We talked about John Clauser and how he designed experiments to test these Bell inequalities. We also talked about the loophole in his experimental setup and how Alain Aspect went on to refine this and make overall a experiment and sort of tightened that gap. And so we could more firmly say that hidden variables were not the reason this was happening. And then last but not least, we talked about Anton Zeiliger, who truly made it very obvious that there were no hidden variables involved. We can control the different ways things are reaching detectors with signals we have no possible way of influencing, like random number generators or random emissions from far off galaxies, and that this does hold. Quantum mechanics, as freaky as it is real and is what governs us at very small scales. And he also pioneered the field of quantum information science, which leads us into our last point, the sort of, now that we have quantum information science, now that we can store and understand more quantum information with this phenomena, how do we use it? And this is what brought us into quantum computers, one of the main applications of quantum mechanics at this point. No offense to anyone else who studies any other part of quantum, this is just what I'm interested in. And we talked about different kinds of problems we can solve with quantum computers. And the fact that I'm very excited about our so-called quantum future. With that is where I leave you on this. I think I ran a tiny bit short. I'm so sorry. I'm about 5 minutes fast. I was just very excited. And with that, I would love any questions anyone has for me. And thank you so much for coming to my talk.
Yeah, thank you so much, Ella. It's exciting to hear sort of an accessible explanation for this year's Nobel Prize discovery. So before some of our participants drop off, I will just mention that the next Unboxing Quantum is yet to be scheduled, but please stay tuned. There should be another 1 or 2 coming up before Christmas. And I'll now turn things over to the Q&A. So yeah, please do, if you have any questions, please go ahead and pop them into the Q&A or the chat tab, and we'll try to get through as much as possible. So our first question is from Brian and Beth Templeton, and it's actually my question as well, which is, in the lab, how do you entangle two particles?
Great question. So according to the Nobel Prize Pop Science article they published alongside of this, you can do it by basically having, like, they literally refer to it as a special crystal, and you blast it with a laser, and you can, like, kick off entangled particles that will leave in pairs, just based on the actual, like, configuration of the crystal itself. The things that are emitted from it will be entangled. I don't know more than that beyond that. But yeah, fundamentally you can excite them off like a substance with a specifically powered laser.
And in this case, the types of particles we're talking about are actually photons, right?
Yes. Yeah, so you can entangle photons. There are other particles you can entangle. As I mentioned, you can even get up to, like, there have been experimentally entangled, like, very small pieces of diamond. But in practice, photons are kind of your best bet.
So we had another question in the chat from Suraj. Asking, can two particles of different origin be entangled? And I asked as a follow-up whether that meant two different types of particles. And the response to that was not common origin except for pair production, which I have to admit I'm not still completely sure what that means.
I don't think I fully understand the question either. Could you maybe rephrase that in the chat? Are you asking if, like, two different particles that are, like, because you could, okay, so two things. You can entangle particles that are not spawned in the same place in space, but you can also entangle particles that are not in, that were not, you know, created in the same place in time, which is quite odd. Is that what you're kind of interested in? Let me just give my yes, no, see if I'm on the right track.
I guess I would ask, can two fundamentally different particles, like, can you entangle light with matter?
Ooh, that is so far beyond my pay grade. I have no idea, but that's a really interesting question. I've only seen it with two particles that are the same, because you want to be able to make sure that, like, the, you know, some intrinsic part of them that you are entangling is possible. So if you're looking to, like, entangle two photons, you want to make, or like two electrons or something, they have, like, the same spin, and that is often what we're entangling. Like, that piece of them is the same, like, that we're looking to, like, measure out of the other one. I have no idea if you could entangle, like, light and matter, but that's fascinating.
Yeah, I don't know the answer either. Our next question is from Patrick, asks, once two particles are entangled, are they entangled forever?
We'd like to think so, but no. So there's a thing called decoherence, where things can, well, they can fall out of, like, their superposition, but also they can, like, lose each other, depending on, like, the state that they're in, what they're influenced by. So ideally, like, not forever, but if they're kept under, like, good conditions, like cold and away from stuff that would mess with them, you can keep them entangled for a long period of time. It's just that there's so much noise and junk in the universe that tends to knock things out at long distances, which is one of the reasons that, you know, the idea of, like, interplanetary communication is not as easy as, oh, well, we'll just put some entangled particles on Earth and we'll put some on Mars and they'll be that way forever, because there's so much stuff that wants to whack into them and mess it up. We are getting better at keeping them stable for long periods of time and over long distances. But yeah.
And when you say long times, can you give a sort of, is that like days or hours, seconds? What's long for entanglement?
Good question. I would imagine on the scale of, like, minutes kind of thing, maybe seconds. I don't know if they can go longer than that. I don't know if we've ever had a stable enough environment to keep them entangled for significant periods of time.
Great. I think this relates quite nicely to the next question, which is, are there current efforts to make quantum computers more publicly available or integrate them with our mobile devices?
Ooh, I get to talk about something. I do that directly. I wonder if that was someone I worked with. So yes, so the idea, I think, that a quantum computer will one day be like a laptop or a smartphone that a lot of people have accessible to them. Just based on like, and I don't know if I just sound like someone in the 1980s that were like, computers will never be smaller than a room. But at this point, quantum computers are huge. They require really specialized cooling to make possible. And they take huge amounts of power to draw on. So if you like plugged it into your house, it would nuke your local grid. So the idea of everyone having one in their home, unlikely. However, the internet, that wonderful and terrible place, exists. And so we actually do a lot of computing on quantum computers right now via the cloud. And so I'll get to the mobile aspect in a second. So right now there are like APIs you can use, or like packages in things like Python that will directly call particular quantum computers. You have to have like a token for them, like it's a service that you pay for, but you can access them. For instance, like my program, actually, I can do a demo for you right now. My program has this thing called the Quantum Hub that we have different sort of games and demos on that let you try different things. And so if I'm going to share my screen again, we're going to all do a little tour on this existing. So right now, this is the Quantum Hub. It is just hosted on Heroku. It's a web app platform. This particular game is just an optimization problem where you look at placing two colors on a grid and minimizing clashing. It's a gamified version of the maximum cut problem. I'm doing really badly at it. Let's pretend this is my solution. It's not great. And so currently I have 10 or 9. I think I actually made it worse by changing that, whatever. Here I can hit get the quantum solution, and this little solver kicks off. And this right now is actually sending my data to the queue for one of the D-Wave Leap computers, and it has returned to me a different solution that is now being displayed here. So this is actually the most common way we currently access quantum computers, because again, just physically they are difficult to access. So with things like this API, we can call them as needed and access their services that way. As it comes to mobile stuff like that, again, we had a pilot app. We were looking at that completely ran on a quantum computer, but the question I would pose back is, what are you looking to solve? Or what are you looking to try to render that you need a quantum computer for? So there are things that we could do. For instance, if we had some sort of like mini game like that, and we're looking to see some sort of solution to it, or there's a problem we're trying to solve with it, that you could totally do mobile to quantum computer. I have an API for that we've tested it before, and it works. Practically, if we started just like given the number of quantum computers versus the sheer number of devices, the queue does start to lag when you start sending huge amounts of information in. So we can do it. It's just that classic Jurassic Park line of like, we could, but should we? And so it's sort of currently being used as sort of special use cases, much like supercomputers, where it's like you get time on them when you need time on them. As opposed to it is helping me beat my friend in Scrabble and finding the optimized solutions that way.
Okay. Our next question, which will be our last question, unless we get any others in the meantime, is can entangled particles be used to send information? And how would you send information between entangled particles?
So yes, not necessarily sending information in the way I think a lot of people imagine it, but it is one of the sort of candidates for like, if we ever did have a colony, God knows where in the universe, how would we effectively communicate with them? And so you can sort of send information, but more what you're doing is making measurements on your end of the entangled system to change their end of the entangled system, and you have to have established at some point what those measurements mean to each other, because you are going to make those instantaneous changes to affect their end of the system or vice versa. So with like established, like if I measure this to be spin up and there goes to spin down, and we've established that, hey, when I measure it this way, I mean this thing, then yes, we can do that, which is freaky and weird because it seems to send information faster than the speed of light, which is a big no-no. It doesn't, but the way it doesn't is ridiculously complicated. So yeah, this is like a potential candidate for like, how do we communicate with, satellites or Mars rovers in real time? So right now, every time I want to move a Mars rover, it takes like a 20-something minute round trip of information because we have to send the signal out there. The Mars rover has to do something, it has to send the signal back that it did it, which is why it goes like 100 meters in 2 months. Obviously not effective. And so this is kind of one of those candidates where we start looking at like, okay, can we use this measurement system to start doing things faster? I find it super interesting. Currently, not a lot of quantum stuff is just super sick in theory and hasn't been put into practice yet. I will be unsurprised if we see this in practice in the next 10 years.
Okay, thank you so much, Ella, and thank you to our participants for the lively Q&A and for coming out to hear about spooky action at a distance. As I mentioned, please do stay tuned for the next Unboxing Quantum event, which will be announced hopefully in the next couple of days or weeks. And with that, I will wish you all a great night and a happy spooky season, a happy Halloween.
Happy Spooktober, everybody. Goodbye.